Hi everyone, I'm Aina. So today I'm going to explain the cloud chamber experiment. So first is to set up the DIY chamber experiment. As you can see the picture, this is the apparatus that we use: container, cloth, dry ice, torchlight, black cardboard, isopropyl alcohol, and gloves. So to make it simple, first we soak cloth with the alcohol and stick it to the inside the wall of the container. Then we place the container upside down over dry ice, as you can see the picture here. And we also use black background and torchlight to make the track easier to see. So the next one is to set up the chamber, which is the more advanced version. We use aluminium base and apply 5 mega electric volt electric field to guide the particle more clearly. So here is the dry ice we put inside the chamber to form super saturated layer, and then this is the picture of the cloud chamber. That's all from me.
So right now we are going to talk about the observation for the DIY cloud chamber experiment. The power for the photoelectrons, electrons of positrons, muons and antimuons, muon transformation, as well as alpha particles was being observed. However, it is hard for us to take a photo as the black cardboard is not fully covered and our camera having very low resolution. At the same time, there will be a reflection of light source at the surface of the container. It can be observed clearer by using our naked eyes. So this is the observation and the picture that we have captured. For the first and fourth picture, we have a very straight line. It can be electrons, positron, muons, or antimuons. However, we can't really differentiate them between electrons and muons due to the low resolution of the camera. The second one is muon transformation. Third one is the photoelectrons. However, the photoelectrons picture is not clear.
I am Mayvin and I'll be talking about the second observation of our experiment, particularly about the observed tracks of different particles. We observed straight tracks particularly due to the ionization of the isopropanol molecules from high-energy muons or electrons and protons. In addition, king tracks were also observed due to the transformation of muon into electrons, antineutrino, and muon neutrino. Curly tracks due to the photoelectrons produced by the photoelectric effect or the electromagnetic scattering of electrons were also observed. Lastly, alpha particles produce thick and short parts as they are highly ionizing right before gaining 2 electrons and becoming a helium atom which escapes to the atmosphere.
In our experiment, we used an AI tool called RoboFlow Demo to identify and classify the different particle paths within our cloud chamber. Initially, this seems promising, especially when we tested it with sample cloud chamber footage from controlled environments. However, when applied to our DIY cloud chamber, the AI's performance was noticeably less effective. Our major limitation was the camera resolution. Our setup lacked the clarity needed to precise detection. But more significantly, the physical condition of the container affected the AI's accuracy. The chamber had minor scratches, reflections, and condensation, all of which the AI mistakenly interpreted as particle tracks. Even our more refined second chamber, although the AI showed slightly better performance, it still confused non-particle artifacts like base reflections and surface imperfections for actual paths. This indicates that the current AI model has difficulty distinguishing real particle events from background noise, especially in non-laboratory environments. For future improvements, the AI should be trained on more diverse real-world datasets, particularly from DIY chambers. Principal component analysis could significantly improve results by helping to reduce this visual noise and extract more robust features of actual particle paths before feeding the images to AI. This pre-processing step would make the AI's jobs much easier, allowing it to focus on real particle events rather than distractions.
Hi and good day, Doctor. I'm Ong Boon Tong. So I'll be discussing the difference between the DIY chamber and the lab cloud chamber. In our observations, the DIY chamber doesn't produce obvious ionization tracks by the particles, but the cloud chamber produces significant ionization paths. This is due to the applied potential difference in the cloud chamber, which is at 1.5 kilovolt. The voltage will create an electric field to accelerate all the free-moving charged particles like muons, electrons, positrons, and protons towards the bottom side of the chamber walls, and the chamber walls is cooled by the ice. The charged particle will ionize the alcohol vapor along their paths. The alcohol vapor will then condense on the ionization paths due to the low temperature, forming visible tracks. But as compared to the DIY chamber, the charged particles are moving freely, thus the ionization reactions only occur spontaneously. So that's all from me. Thank you.
In conclusion, it is easier to observe our experiment results for the DIY cloud chamber. using naked eyes than a phone or AI tool. This is due to several reasons, such as the reflection of light source, the small area of the black cardboard, and lastly, the camera resolution, as well as the path vanishes very quickly. So, thank you.